Well, welcome everybody. I don't have the test graded yet. I had another class in front of yours I'm still trying to finish. I'll get those as soon as I can. In the meantime, we want to go ahead with chapter 7. I've said before, I think this is the most difficult chapter of them all. This is on trigonometric identities. I'm going to do a little review today because the test sort of put us maybe a little distant from what we were covering. Remember, we were using our trig identities to simplify trig expressions, to prove new trig identities, and to be able to find trig functions of new angles. The last ones we were looking at were these sum and difference identities. And these are important that you memorize them. They're used in a lot of your higher science and math classes. If we take sine of x plus y, recall, that's sine cosine plus cosine sine. Hopefully that looks familiar. I want to make sure you know that one. One of the reasons these are real important, besides that they're used a lot, is actually we're going to be able to prove some additional identities from these. And if you can memorize these, the others will be able to figure out when you have trouble with those. Now there's another one here. If we put a minus here so that we subtract two angles, then that just puts a minus here. So we can memorize two identities at once. Sine of x minus y is sine cosine minus cosine sine. So plus goes with plus, or minus with minus. This is two identities in one, we said. Let's call that equation 1. We're going to have 9 of these by the end of today, but 3 of them are review. So it's only 6 new ones, but you'll start to, I guess, somewhat befuddling by the time you get through all these. There's too many identities, but make sure you memorize these, because the next identities follow from these, and the next identities follow from those, and this material builds and builds. And these sections, more than any others, you just need to practice them is the way to get good at them. So here's the sine sum and difference identities, 2 of them. Now we have the cosine sum and difference identities. Cosine x plus or minus y with cosine cosine minus or plus sine sine. So plus goes with minus and minus goes with plus on the cosine identity we said. We'll call those equations 2. And then finally we have some for tangent. Tangent of x plus or minus y was tangent plus tangent over 1 minus tangent tangent. A little harder to remember, I think, and used a little less. And then plus goes with plus and the opposite sign on the bottom, or minus goes with minus on top and the opposite sign on the bottom. That's the way it works. 2 identities there also. All right, now there were a couple of problems we didn't get to with these last time. I wanted a nice review of these. Will be to try a new problem. Here's an example of these that we didn't try before. This is on your homework assignment. Let's see. There it is. It's number 6A. I like doing some of these in class so that you can, when you do your homework, try and work it and then see it. You know, if you get stuck, you can look up how to do the intermediate steps. But I won't do all of these. Suppose I asked you to evaluate what is the sine of the arc cosine of 0 minus the arc cosine of a half. These are the kind of things you run into in practical applications that are not obvious what to do sometimes. But it's kind of like a cookbook. When you see a sign of a difference, think of this identity here. Think, if this is x and this is y, then this is sine of x minus y. I have an identity for that by equation 1. I can write this as sine arc cosine 0 cosine, all right, sine x cosine y of arc cosine of half minus cosine sine. Cosine of the first one, sine of the second one. Okay, so there it is. And part of this is just practicing them enough that you look at them and say, oh, it's sine of a difference. I'll use the difference identity, right? Minus with minus. Now, how do we evaluate these? We can use these on the unit circle. I will say, what's the arc cosine of 0? I know how to do that one. The arc cosine of 0 is the angle theta. Remember, the inverse cosine gives you an angle between 0 and pi, whose cosine is this number. On the unit circle, you look it up and you say, what angle has cosine equal to 0? Cosine is the x-coordinate. Well, the x-coordinate is only 0 at these 2 points, right? Here's the line of all x-coordinates, x equals 0. There's only 2 points on the unit circle where the cosine is 0, so you either have this terminal ray or this one. Now, there's only one of those that's between 0 and pi, right? Our cosine is a function, so there's only one answer, one output. It can't be this one, it's not between 0 and pi, it must be this one, pi over 2. So the arc cosine of 0 is pi over 2, and what we have then is the sine of pi over 2. And then what's the cosine of the arc cosine of a half? Huh?
1/2.
Yeah, it's just 1/2, right? Because this is, they undo each other, right? So this is cosine of the arc cosine of a half is a half. And then minus cosine of the arc cosine of 0. Well, we go back to the picture and we say, this is the point 1, 0. Sorry, 0, 1. The first coordinate is the cosine, and the second one's the sine. The cosine of this angle is 0. It's pi over 2 again. And they undo each other, and this one gives us 0. Right? Cosine of the arc cosine is 0. Or you can say this is pi over 2, and the cosine of pi over 2 is 0. And then finally, sine of the arc cosine, we won't need it because it multiplies 0, but just for practice, we can say, if we take the angle whose cosine is a half, so this would be an angle theta between 0 and pi, since it's our cosine, with cosine theta equal to half. What angle is that? I could come over here. The cosine is a half, halfway across here. Here's the point on the unit, the points on the unit circle with cosine equal to half. You can draw this line, x equals a half. And so it's either that angle or that angle. And this angle is in the wrong quadrant again. It must be this one. Well, if this side is a half, this goes over to x equals a half. And this is 1, and this side has to be square root 3 over 2. The Pythagorean theorem would require that. And the angle must be pi over 3. So just for practice, we'll say this is the sine of pi over 3. Sine of pi over 3 is the y coordinate, square root 3 over 2. So there it is. I think I should write it out. Let's write it out since I did on there. Sine pi over 3. Okay, and now this is sine pi over 2, which is 1 times a half, minus 0 times square root 3 over 2 with that one. And we just wind up with 1/2. There's the sine of this sum of angles. Kind of tricky, but this is pulling it all together. So I think it's a good problem for that. Okay, and there are a couple other problems in here similar to that. I hope that gives you a little bit of recollection on that. Finally, you can verify identities. Because you could take trig functions to new angles and you could verify identities and simplify expressions. Verify or prove the identity that tangent of x plus pi over 4 is actually equal to tangent x minus 1 over 1 minus 10, plus 1, excuse me, over 1 minus tangent x. How about that one? Remember how to verify identities? What you do is you go through that list of steps where you apply algebra, you apply a trig identity, you rewrite everything in terms of sine and cosine, and then you repeat that over and over, starting with getting one angle was the 0th step. So I'm going to put this as we do for these verify identities. I'll put the left side here and try and work both ends towards the middle, just to kind of double my chance of being able to make these things meet. Put this one here, tangent x plus 1 over 1 minus tangent x. See this okay? I guess maybe I'm getting too close to the edge. And I'm trying to get here from here. So the first step, the first thing we said before we get going is get one angle. Well, look, there's two angles. There's tangent x and there's tangent x plus pi over 4. So we'll try getting one angle. That was the first strategy. How can we get one angle out of this? Is we use the sum of angles formula. Tangent of x plus y is tangent plus tangent over 1 minus tangent. Same sign on top and the opposite sign on the bottom. That's how I remember it anyway. You can memorize it your own way, right? So x here and x here, and pi over 4 here, and pi over 4 here replaces y. Now I've gotten it down. I can evaluate tangent pi over 4. Maybe you will recall tangent pi over 4. We can figure it on a circle or on a triangle. Let's just do a triangle. That's easier, right? For acute angles, I usually use a triangle. Here's a pi over 4. And we have this triangle, square root 2 over 2, square root 2 over 2, 1, if you recall, for the 45, 45, 90 triangle. And the tangent is then opposite over adjacent is, this over itself is 1. So this equals 1 for this triangle. What we have then is tangent x plus 1 over 1 minus tangent x. Now I've got one angle. Ah, there it is. What do you know? So I didn't take very many steps for this one. I just had to use the sum of angles formula. But you'll see that when you get these problems where there's not just one angle, but like one of them says 3x and the other says x, that you can use these identities that we have to make the two ends meet and verify new identities. Any questions on that? Anybody online got questions? Okay, I'd like you to be able to do that. And again, on these identities, it just takes practice to see where to go. When you think of that strategy, first thing you do is try and get so it's just tangent x, not tangent of x and tangent of x plus something, right? Now, let's do the fourth one. The fourth one is this. Sine of 2x equals 2 sine x cosine x. How about that? This is called a double angle identity because you're taking the sine of a double angle, right? So this is kind of an interesting point because I see people do this a lot in trigonometry when they're first learning these identities. they'll say sine 2x in the book and they'll rewrite it as 2 sine x. That's not true, right? You can't pull the 2 out of here. The idea is that this is the sine of 2x. It's a function. If you saw square root of 2x, you would just pull the square root of the 2 out of this function and rewrite it as 2 square root of x, right? It's square root 2 times square root of x. You can't just pull the 2 out of a function. Same thing here. You can't just pull it out. The book on it won't always write parentheses because you get tired of it. You just say there's implied parentheses. Just like here, there's actually a 2 for square root, but we don't write it by convention. You can leave it off if you want. So this isn't true. What is true? The 2 doesn't just come out. If you have sine 2x, it's 2 sine x times cosine x, right? So this certainly isn't true. It's only true if cosine x happens to be equal to 1, which would be for the angle pi over 2. That special angle, it happens to work for that one angle, right? So we'll make that note right here. Don't do this kind of stuff. Sine of 2x, the 2 comes out. This is the identity for double angle. Sine of 2x is 2 sine x times cosine x. Let's do the proof of that one over on the side. Proof of 4 is actually insightful because it helps you to remember. When I was a trig student many years ago, this was hard to remember by itself. There gets to be too many identities, right? But if you remember this one, you can figure this one out every time. When I see this one have trouble, I can kind of visualize this one. Oh yeah, so memorize these for sure, and these will lead to the new identities. I said this material will build, right? Here's the proof of this identity. You start with the equation 1 with, you put y equal x. You replace y with x everywhere in 1 using the sum, the top one. And then you have sine of x plus x on the left equals sine x cosine x. Just everywhere I see y, I put x because this works for all x and y. It works in particular when y equals x. Camera over here, yeah. Okay, so there's equation 1 with the y replaced by x. So at this, and now on the left, well, x plus x is 2x. And then sine and times cosine, cosine times sine. You can multiply in either order, right? This is also sine times cosine, so there's 2 of these. There it is. It's a very quick step. You can look at this one and imagine you put x here instead of y. It's got 2 of these is equal to sine of 2x. You can imagine that in your mind. This proof is so short. So there's the proof of that one. Here's another one. Imagine putting y equals x on the second one with the plus sign here. So suppose I want it, then I would get, let's try it over here. I'll put proof of 5, what I'm going to put here. These proofs are good because we're going to be doing identities and other identities. You make your own designer identities with similar proofs, right? If I want cosine of x plus x by putting y equal x in the second one, plus goes with minus on the cosine here. So this is cosine, cosine, minus sine, sine. And everywhere I see x or y, I put x. So the cosine identity, putting y for x gives me that, but now this is 2x. And cosine times cosine, we write this notation as cosine squared, and sine times sine, we write this notation as sine squared. There it is. Again, you can sort of visualize it. Put y equal x, what do I get? That really helps in memorizing these. Cosine of 2x, therefore, is cosine squared x minus sine squared x.
Wait, what is 5? I can't see it over there. I can't see 5 over there.
Sorry, yeah, I moved it over so you can see the proof, didn't I? Let me back it out a little so you can see both. Thank you.
A little over. There it is. Good. That's good.
Okay, so there's this one, and I should point out also that there are two more of these double angle identities for cosine. It's got three of them that people use a lot. We're only going to memorize this one, but there's two others you can memorize if you want. They follow quickly from this one. I'll write them down soon, but I'll just recommend that you memorize this one. These identities over here are all to be memorized, because you need to have them in practice in your later classes if you ever use this again. If you take calculus, you use these, they expect you to memorize them. If you take first year physics, you use these, they expect you to memorize them. First year engineering, same thing. You have to know them all that. And in other classes too. I think chemistry and other places too. It's been a long time since I took chemistry though. All right. So there's that. Finally, I'm not even going to do this one. There's a completely analogous proof. What if I replace y with x in this one and use the plus? Tangent x plus x on the left becomes tangent 2x. All right. And I replace it here. Tangent x plus tangent x is 2 tangent x. Yeah, I can figure it out. 1 minus tangent x times tangent x is 1 minus tangent squared x. So you can figure it out as you go. That's good practice on a short proof anyway. There it is. Just by replacing y with x and these three, we get these three double angle identities. Now, one of the most common popular problems in any trick book, and you'll probably get one of these on your exam, is they'll give you the value of one trig function of x, and then they'll say, what's a trig function of 2x? And you can do all of those that way. So now we made an example of the classic problem here. It's, in some sense, it's not really what you're going to run into when you take your other classes. But it's like you take the piano, you play that silly song, da, 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 da. It's to get your fingers working right and get you, expert at being able to play other songs. Same thing on this. If you can do these exercises, it will help you to be able to do other problems that you will run into. So pardon that this is a little bit of an exercise that doesn't have a lot of applications, but if you're given one trig function and a quadrant, what do we already know that we can calculate? Quadrant for the angle. We know we can calculate all 6 trig functions. Remember that? For instance, if you're given sine, you use the Pythagorean identity to find cosine. Once you have sine and cosine, you can get the others by taking sine over cosine is tangent. All right, cosine over sine is cotangent, 1 over cosine is secant, and so on. So all you have to do is get one, you use Pythagorean identity for another, and figure all the others out, for instance. Now, once you've got them all figured out, well, then you can do any one of those 6 identities because you've got all the trig functions you need. So we can do that. We'll say, give them one trig function and a quadrant for the angle in that trig function. Not only can we find all 6 trig functions, but we can evaluate any trig function of a double angle. So it's kind of like a cookbook. If you're going to make a pie, you need these ingredients. Here's an example problem. Do the easy one here first. Tangent, cotangent are always the harder ones. If sine x is an eighth and x is in quadrant 1, I'll just write Q1. It's over a little here. What is the sine of 2x? Here's how you can do these problems. If I ever see sine of 2x, I just immediately think double angle identity, right? I'll write that immediately as 2 sine x cosine x. Now I only need sine and cosine of x. Well, I'm given sine x, I need cosine. What do I need to do? One thing I could do is, I said, memorize these Pythagorean identities solved for a particular trig function because they come up a lot. Here's an example. I need cosine x given sine x. So I just say immediately cosine x is plus or minus square root minus 1 minus sine squared x, right? By the Pythagorean identity solved for cosine. So I write the double angle identity and I said I need cosine, so I'll compute it. Is it plus or minus? This is where the quadrant comes in, right? Quadrant 1. All trig functions are positive in quadrant 1, so I put plus. So this is square root 1 minus sine is an eighth squared. Now, a lot of these problems, actually, the algebra again is harder than the trigonometry, unfortunately. That's just the way it is. Square root. This is 1/64th, and I'm subtracting, so I need a common denominator. Let's write 1 as 64/64. And now this is square root of 64 minus 1 is 63 over 64. And you reduce that because 64 is a square. We write this as square root of 63 over 8. Right? Square root of the quotient is the quotient of the square root. Square root of 63 over square root of 64. And square root of 64 is 8. There it is. There's the cosine. So now I'll put in this as 2 times 1/8 times square root of 63 over 8. But that's what you can do on all these. Write down the double angle identity, figure out which trig function you need and compute it, right? And then plug it in, right? Now we multiply this out. To multiply it out, just write this as a quotient, 2 over 1. It's top times top times top over bottom times bottom times bottom. It's 2 square root 63 over 64, right? When we multiply all these out. And now we notice we can reduce it. Square root of 63, this is square root of 7 times 9. If 9 is a square, so I said really write this is 3 square root 7. And then 2 over 64 is 2, there's a 2 canceling, it gives me 1 over 32. So I can write this as 3 square root 7 over 32. There it is. I have 2 times 3 times square root 7. 2 cancels part of the 64 on the bottom. There it is, 3 squared 7 over 32. That's the answer I want to see in the test. If you leave it here or something, I'll take a little off for not simplifying. Any questions on that one? Work? You want to be able to do this, given a trig function in a quadrant, or the trig function and a sign of another unrelated trig function will tell you the quadrant. Sometimes that's done. You want to be able to find any trig function of a double angle. For instance, now, what is the cosine of 2x for the same case? Well, we have that identity. It's cosine squared minus sine squared, right? Just immediately see sine cosine 2x. Just write this down. Now I computed cosine on the bottom here. So cosine is square root 63 over 8. Square that, and then sine was given is 1/8. So I square that. Evidently, I've got 63/8 minus 1/8. This will be 62 over 8, and I've reduced that to 31/4. There exactly is the cosine of 2x. And then you can find tangent 2x similarly. I'm going to do that for the next. Okay. Maybe if I turn that too quickly sometimes.
I didn't quite get that.
Okay. Sometimes I go backwards, writing across the board for just that reason. That should be on there. I'll just go right to left here again. I'll leave that last part. Now, here's another one. Suppose that tangent of x is -8 and x is in quadrant 4. Suppose this time I said find cosine of 2x. This is a little trickier. Why is it trickier? There's multiple ways to do this actually. But what you need to do is just say, I'm trying to find cosine 2x. I go to the double angle identity immediately. So that's cosine squared minus sine squared of x. So I need sine and cosine of x from tangent. You can do something like use the Pythagorean identity with tangent and secant to find secant, and then use secant to find cosine, and cosine to find sine. That's fine too. I won't be picky which way you do it. I like to do it this way. I like to say if tangent x is -8, I can write that as a quotient, -8/1. And then I can write that quotient as a quotient of points on the unit circle, right? -8/1 is on the unit and not on the unit circle. This is way outside the unit circle, -8. But if I divide through by the root sum square, -8 squared plus 1 squared square root, that's square root of 65. I can write this as -8 over square root of 65 over 1 over square root of 65. Right? Using just dividing the top and bottom by the same number, so it's the same quotient. But now this is a point on the unit circle. When you divide by the root sum square, then this squared plus this squared equals 1. Right? And if x squared plus y squared equals 1, that's a point on the unit circle. This is the equation of the unit circle, right? So you divide by the root sum square to make the sum of these squares equal to 1, a point on the unit circle. But there's another option. What else could it be besides this ratio on the unit circle? This is the trick. This one. I can take the top one positive and the bottom one negative, right? Just so it's the same quotient. So it could be like that. Well, these are the only 2 points on the unit circle. Divide by root sum square on both. And then take minus this one over minus this one. And those are the 2 possibilities. This might be sine, and this might be cosine, or this might be sine, and this might be cosine. Which one is it? That's where the quadrant 4 comes in, right? X is in quadrant 4 means that cosine has to be positive. You can picture it in your mind, right? An angle over here in quadrant 4 drops on the unit circle, and the cosine x coordinate is positive, the sine is negative. So I want x positive, cosine, and y negative. That's this one. This is in quadrant 4. This one is the opposite quadrant in quadrant 2. All right, what that means is that this is sine and this is cosine. Right, tangent is sine over cosine. To be in quadrant 4 and have this ratio, it has to be these 2 numbers, y and x coordinates on the unit circle. So if you mark this point, this will be -8 over root 65. And this would be, should make the angle better, I guess, like that. And a 1 over square root of 65. There's the angle x. Anyway, so you don't need to draw this picture, but the idea is maybe if we leave it off for just that reason. But you can do this, it always works. All right, once I know sine and cosine, then I'm home, right? Because Cosine squared minus sine squared is then, let's see, here's cosine, right? The tangent is sine over cosine, so it's cosine and this is sine. Is minus 8 over square root 65 squared, that's cosine squared, minus sine squared, 1 over square root 65 squared. Well, let's see, this is 64 over 65, this one, minus 1 over 65, this one, gives us 63 over 65. Is that visible, I hope? Yep, okay. So there is cosine of 2x given tangent x, half the angle. Yeah,
Are you sure cosine is equal to negative 8 over 65?
sine should be negative 8. Did I write it backwards? Oh, I wrote it backwards, didn't I? Thank you. Yeah, that's sine and that's cosine. I wrote it backwards. So this one should have been 1. And this one should have been minus 8. And now I've got 1 minus 64 is minus 63 over 65. It doesn't help to do, it doesn't hurt, I was going to say, to do a check on these things. Sometimes just to see if it seems about right. Thank you. Okay, so there's that one. Now the next step to do is to say that if we can do double angles, we can do half angles. If you really think about it, if given the a trig function of an angle x, I know all trig functions of 2x, and I must be able to go backwards and from angles 2x go back to angles x, which are half that big. So let's try that. I think I can move this now. And here's what you get. Let me derive it as follows. Now, from equation 5, we said we would go back and find 2 more double angle identities for cosine that you'll see in the books. And I don't expect you to memorize these, but I do want you to have seen them because you'll see somebody use them. You don't want to say, where did that come from? I didn't learn that in my trig. I don't want that to happen in my class. Let's say this. From equation 5, we have the cosine of 2x is equal to cosine squared x minus sine squared x. But by the Pythagorean identity, right, sine squared plus cosine squared equals 1. Cosine squared can also be written as 1 minus sine squared. So this is just because of the Pythagorean identity. This is sine squared plus cosine squared equals 1. Right? If you subtract the sine squared, you got cosine squared is 1 minus sine squared. Maybe off the screen just a little, is it? I think it's okay. So this cosine 2x is actually equal to 1 minus sine squared is 1 minus 2 sine squared x. This is a trig identity that you'll see occasionally. Instead of cosine 2x is cosine squared x minus sine squared x, they might write it this way. I think this comes from taking the first one and putting the Pythagorean identity. Also, maybe I should call this 5a. It's an alternate double angle identity. And similarly, cosine 2x equals cosine squared minus sine squared, equation 5 again. This time, let's use the Pythagorean identity to replace sine squared with 1 minus cosine squared, right? Subtract sine squared here, you kind of visualize. I'm sorry, subtract cosine squared, you can kind of visualize. You get sine squared is 1 minus cosine squared. So let's replace this one also by the Pythagorean identity was 1 minus cosine squared x. And now I've got cosine squared x plus cosine squared x. There's two of those. Minus 1. This is the other double angle identity for cosine that you'll sometimes see. And you don't have to memorize. But from these, now we can get some nice things. If I call that 5a and 5b alternate double angle identities for cosine, we can say in 5a, put or substitute 2x equals theta. Theta equals 2x, right? In which case x is 1/2 theta, dividing by 2. Yeah, what does this become? Well, let's see, this becomes cosine theta equals so 2x is theta, 1 minus sine squared, and x is 1/2 theta. I can solve that for 1/2 sine of 1/2 theta as follows. I can add sine squared over here and subtract cosine over here and get equivalently that sine squared 1/2 theta is oh, I'm sorry, let's see. Should have been 2 sine squared. I forgot 2. 2 sine squared 1/2 theta is 1 minus cosine theta. I subtract this one over and add this one over. And then divide by 2. And I've got sine squared theta is 1 minus cosine 1/2 theta. Is 1 minus cosine theta over 2. From which I now figure the sine of half an angle by square rooting, right? And you have to be a little careful here. If I gave you an equation, x squared equals 4, you wouldn't just say x equals square root of 4 is 2, would you? What would you say? That's part of the answer. But there's two answers, right? There's two numbers whose square is 4. This radical sign means the non-negative number whose square is 4, but there's also a negative number whose square is 4. That's minus 2. There's two solutions, right? We put plus or minus 4. We call 2 the principal square root of 4. So there's two solutions. When a square is equal to a positive number, there's two solutions. The positive number whose square is that number, and the negative number whose square is that number. Same thing here. If I put sine squared equals this positive number, well, we know it's non-negative at least because cosine is never bigger than 1. So never subtract it, make it negative. By taking the square of both sides, we then get this one, which I'm going to call equation 7. Says sine of 1/2 theta be plus or minus the square root of the right side, just like here. There's equation theta. It's a half angle identity. Sine of 1/2 an angle is plus or minus the square root of 1 minus the cosine of the whole angle over 2. Also, in 5b, substitute in theta equals 2x and x equals 1/2 theta. To get similarly, let's see in 5b here, cosine 2x becomes cosine theta. And it's 2 cosine squared x is 1/2 theta minus 1. Now I'll add 1 over. I'll make the equivalent equation 1 plus cosine theta equals to cosine squared 1/2 theta. I can divide by 2 and switch sides. So I'll switch sides and divide by 2 and get cosine squared theta is 1 plus cosine theta over 2. And now if cosine squared is this, then cosine is plus or minus the square root. Cosine theta equivalently plus or minus square root. This is 1/2 theta. I'm sorry, this copied it. Cosine of 1/2 theta is 1 plus cosine theta all over 2. There's equation 8, a half angle identity. Cosine. Cosine of half an angle given cosine of the whole angle is this. And then you can probably get this one. Ninth one is going to be this. I wonder what the tangent of half an angle is. The easiest one I know of, this one is not used so often, so I prefer to pick the one that's easiest to remember. Is we know tangent is sine divided by cosine. So we just take this one divided by this one. The square root 2's cancel, right? This one over this one, the square root 2's cancel. And you just get square root, and you get this answer, plus or minus square root 1 minus cosine theta over 1 plus cosine theta. And this one you get by dividing 7 by 8. 7 over 8 equals tangent 1/2. So this one divided by this one, the square root 2's cancel, and you get this one. That makes this one kind of easy to remember. I always had trouble remembering the harder ones. There is another half angle identity for tangent. I think it's not worth doing. This is the one that's easy to remember, and you can figure out the other ones when you do. All right, so we've got 9 identities, new identities for trig so far in this chapter. 3 of them we had before tonight. That are sort of doubled, so in some sense we have 12, I guess. Okay, so now it's the same kind of thing. Given one trig function in a quadrant, we can now find any trig function of half an angle. It's the same thing. Given a trig function in a quadrant, or you can figure a quadrant for its angle. Trig function value, if you like. We can find all 6 trig functions, and then we can use them to evaluate half angle identities. So we can evaluate exactly, not just with a calculator approximation, any trig function of half that angle. Strategy is the same. You can find all 6 trig functions. However, in this case, you only need one. Can you see that? You only need the cosine. Equations 7, 8, and 9 to calculate a trig function of half angle only need cosine. So you can just do that one. So we could say this instead of evaluate any trig function, we can say we can evaluate cosine. Oops. And any trig function of half the angle. Using cosine. It just says cosine. So let's try one of those. All right, so here's a good problem then. Suppose that sine of x is minus 12 over 13 with x in quadrant 3. Let's find cosine this one tells you to find all three. Let's just find the cosine of 1/2 x. When you see cosine 1/2 x, you should immediately think, oh, I should use a half angle in it, right? So I'm going to use this one here, equation 8. I guess I'll erase these. But one thing that's important to point out on these, you should notice, these are all real easy to remember. It's 3 new identities, but look, these two are the same except for the minus becomes a plus. They're both cosine in here. 1 plus cosine over 2 square root, 1 minus cosine square over 2 square root. It's just the difference between putting a plus or a minus. And this one is just the one divided by the other, so we figure it out even. So these are not so hard to remember, all three of them. You just remember these with change between minus and plus. And then this one's their quotient. Well, I like that about these. They aren't so hard to remember. Here's what you do. If you're asked for cosine of 1/2 x, immediately write down the half angle identity. It's plus or minus the square root of 1 plus cosine, put x over there, didn't I? X over 2. There it is. So there's the cosine of 1/2 x. And what you're thinking in these half angle identities is no matter what trig function they give me, I just have to find cosine of that angle and plug it into the half angle identity. So I need sine, let's do 1/2 x. I need cosine of 1/2 x. This identity is, okay, sorry. If sine x is minus 12 over 13, I need cosine x. We'll say since cosine x is plus or minus square root 1 minus sine squared x by the Pythagorean identity solved for sine. I said, or cosine, I said we use this a lot. Since this is the case, and sine is minus 12/13, because I'll have to erase this now. We already used it. We can compute this. I have this. Is it plus or minus? X is in quadrant 3. Sine and cosine are negative in quadrant 3, so it's negative this time. Now we have square root minus the square root of 1 minus, and sine is minus 12/13. And I'm going to square that. So this is 144 over 169 if you remember your squares. Minus the square root of 1 minus 144 over 169. And here's that algebra biting us again. It's going to be harder than the trig here. I'll just write 1 is 169 over 169. And now, let's see, 169 minus 144 is 25. So it's square root of 25 over 169. Oh, that's easy. This is just 5/13. If you remember the square. Square root of 169 is 13. Square root of 25 is 5. There's the cosine of x. And here's what I like to do on these is when I have to find the cosine of 1/2 x, I write the identity. Then on the side over here, I calculate the cosine of x that I need. Minus 5/13. Now I can just go back and plug it in. Cosine of 1/2 x, is it plus or minus? It's tempting to say, wait a minute, we're in quadrant 3, cosine is negative, but it's not clear, right? X is in quadrant 3. When I take cosine of x, it must be negative, but 1/2 x, where is that? Over on the side somewhere, you calculate this. Quadrant 3 means that 180 degrees is less than x is less than 270 degrees, right? So x is in quadrant 3 means this. Now you divide it by 2 to see what quadrant 1/2 x is in. So 1/2 x is between half these numbers, between 90 degrees and 135 degrees. Well, that, if all these angles are in quadrant 2. not quadrant 3. So you figure it's cosine positive or negative in quadrant 2. Always look at this angle, right? What quadrant is this in? We have to choose negative still. There's what it is, it's quadrant 2. Cosine is negative. Now we computed cosine down here, so we put it in. This is minus square root 1 plus minus 5 over 13 square, minus 5 over 13 over 2. 1 plus cosine x. And you can't leave it here, right? This is going to be a couple points off if you leave it like that. Compound quotients, right? Quotient with a quotient with a quotient. So what do I do to get rid of the 13 here? I multiply top and bottom by 13. So I'll take the top and multiply by 13. The bottom by 13, so I don't change the quotient. Now what I have is minus the square root of 13. This time this is minus 5 all over 6. So this is minus the square root of 8 over 26, which is square root 4/13, or 2 over square root 13. This is minus 2 over square root 13. Is the cosine of 1/2 x. This is a good answer. I'll take this on the test. However, if you look at the back of the answer sheet there, they'll rationalize it. That's a good answer too, of course. This is what's in most textbooks. Multiply top and bottom by square root 13 and call this minus 2 square root 13 over 13. You rationalize. I'm sorry I kind of ran that problem together here, but this is the way I think is a good way to do it. Evaluate cosine 1/2 x. Write out what it is by the half angle identity. Whenever you see this half angle, write the half angle identity. Then figure out what you need. Cosine x is that, and plug it in. That's all there is to those. It is tricky, I guess I should say, because you have to figure out what quadrant half the angle is in, given the original angles quadrant. Well, we can now actually do some trig functions of new angles. Before we used the sum and difference identities to evaluate trig functions of any multiple of 15 degrees. Now that we have half angle identities, we can do trig function of half of any angle that we already knew exactly. So if we can do 15 degrees, we can now do trig function of 7.5 degrees, or 3.75 degrees, or half of that exactly, with a lot of work. I'm not going to make you do that on a test, do half of a half of a half. But the idea is that theoretically we can do that. So you have to memorize the identities. I'm going to have you write out your work to show you can do them, even though your calculators will do these half angles exactly on a lot of calculators, and you can check your answers that way. I want you to show the work, because I could have asked you to do half of a half, and the calculators won't do that exactly. I can do those tricky questions, but the test is too long and too many numbers. It's easy to, make a mistake somewhere. It's better on testing just to stick something similar in there that you can check on your calculator. So now we can, let's write this out, evaluate any trig function exactly if we know if it is half of an angle, not necessarily a special angle, but an angle that's special, or half of that, or half of that, or half of that. If it is half of an angle, lose trig functions, we know exactly, all right. Right. So here's a nice example. Find exactly what is the sine of 22.5 degrees. Wonder what that is. That's not a special angle. It's got a half a degree in there, right? But it's half of 45 degrees. So I rewrite it as sine of 1/2 of 45 degrees. And now I can apply the half angle identity. Once I see the sine of half an angle, it's plus or minus the square root of 1 minus cosine of the whole angle, 45 degrees over 2. And what you observe is, in order to evaluate the sine of 22.5 degrees, I only need to know the cosine of 45 degrees, a special angle. This value I know, right? Is it plus or minus? You go back to the original quadrant and say, this is in quadrant 1. So I'm expecting for any trig function to get a positive answer. Well, but plus. I have square root of 1 minus, remember cosine of 45 degrees is square root 2 over 2. There it is. There's an exact answer. And yet I'm going to take off a point or two on the test. Because it's not simplified. Again, you see a compound quotient, a quotient of a quotient. So I'll have to get rid of that compound quotient. How do I get rid of it? I multiply through by the least common denominator that I see of any denominators that are present. There's only one. I just need to multiply through by 2. So let's write this square root of, and I'll multiply the top, 1 minus square root by 2, and the bottom by 2. Balance it. That's what's quotient. Now this times this, we have 2. These two cancel, and you get minus square root 2. And the whole thing is over 4. Evidently we have, well, square root of 4 is 2 is known, so we'll write this as square root of 2 minus square root of 2 all over 2. There it is exactly. Now I should make a note at this point, but actually a lot of these square roots with square roots inside reduce. So this actually may reduce, but I won't require it. It starts to get too much tedious algebra. It's all right to leave these square roots as square roots. I'll just point out that sometimes it does reduce. All right, here's another one. What is the sine of 165 degrees? How about that one? Can I do that exactly? How do I know? I know I can do it exactly because 165 degrees is a multiple of 15. And how do I know that? The way I usually figure these out is if all the quadrantal angles are special angles, right? They're all multiples of both 15 and 45, 30 and 45 degrees. Sorry, I should say all the quadrantal angles are multiples of 15 degrees. And so if I'm 15 degrees off from a quadrantal angle, like 180, then I know that this must be a multiple of 15 also, right? 180 is a multiple of 15, all quadrantal angles are. And so this one, less 15 degrees is also. So I know that's a special angle, a multiple of 15 degrees. I already know from the sum and difference identities that I can do this with a sum and difference identity, but let's do it a different way. Let's do it this time using the half angle identity. It's over a little. So we can do this with the half angle identity. What if we want to use, or with the sum of angles identity? What if we want to do it with the half angle identity? It turns out that all multiples of 15 degrees are half of a special angle, so you can also use the half angle identity for them. So let's rewrite this as sine of half of 330 degrees. Right? And you recognize immediately probably that 330 degrees is special angle. It's 30 degrees from the quadrantal angle 360. Right? So this is a special angle. half of any special angle I can do exactly. I just use this half angle identity and say the sine identity is square root 1 minus cosine of the whole angle, 330 degrees, 2. And now I just have to do this cosine of a special angle. And I've got so these half angle identities also allow you to do exactly a trig function of any multiple of 15 degrees. Interesting thing comes out though, sometimes it doesn't look like the same answer, even though it is. Let's try this. What's cosine of 330 degrees? I go draw the unit circle. Oh, and by the way, is this plus or minus? What should it be? You might say, oh, 330 degrees is in quadrant 4, it's over here. Sine is negative over there, and you'd be wrong. Why would you be wrong? The answer is this is evaluating not at 330 degrees, we're evaluating the sine of 165 degrees over here. So find the quadrant for the original angle, 165, and say in quadrant 2, sine the y coordinate is positive. So I want plus for quadrant 2 for 165. I don't want the quadrant for 330. All right. So now this is plus the square root of 1 minus cosine 330. Now I want to draw the 330 degree angle. Evaluate cosine. Cosine of 330 degrees, there it is the x coordinate here when I drop a perpendicular. Well, if that's 330, this is 30. And this side is 1/2, right? And this side is square root 3 over 2. And so the cosine is the x coordinate, square root 3 over 2. So this is 1 minus square root 3 over 2 all over 2. Like that. There's the exact value of sine of 165 degrees. But once again, it's a couple points off because this requires a lot of reduction and it's worth more than 1 point of the problem. I'll multiply top and bottom by 2, the biggest denominator I see. I should say the least common multiple of all the denominators I see, and there's only this one. So I multiply the top by 2 and I get 2 minus square root 3. I multiply the bottom by 2 and I get 4. Evidently the answer here is square root 2 minus square root of 2 minus square root 3 all over 2. It is exactly. Now just for a check, maybe I want to go do this. Let's check it. I know also that any multiple of 15 degrees can be done by the sum of difference right now. So I could do it this way. Sine of 165 degrees is sine of 120 plus 45, the sum of two special angles. Well, I can use the sum of difference, I guess, the sum identity to evaluate that. Let's see what we get. Again, I'm thinking of this is x and this is y. Sine of x plus y is sine cosine plus cosine sine. And then for non-acute angles, you have to go to the unit circle. Draw 120 degrees, about like that, 30 degrees past this point. That leaves 60 degrees over here to make a straight angle. I drop the perpendicular. This is a half. This is square root 3 over 2. And I observe the coordinates at that point are minus a half plus square root 3 over 2. That must be the cosine and sine respectively, 120. So the sine is square root 3 over 2. The cosine is minus a half. And now sine and cosine of 45 degrees, I just use the special triangle. I don't need to put up any circle. This one has sine square root 2 over 2, square root 2 over 2, and 1. So the cosine is this over this is square root 2 over 2. The sign is this over this, is square root 2 over 2. And what do I get? I get square root 6, this times this, over 4, minus top times top is square root 2, minus comes from here, over 4 is square root 6 minus square root 2 all over 4. And to my horror, it looks different. What's wrong? So I go check this on my calculator, and I'm going to compute it here. Square root 2 minus square root 3 all divided by 2, and I get 2.588, blah, blah, blah. And then I compute this one, just to see how they compare. Clear this off. Square root 6 minus square root 2. That number, then I'll divide that by 4, and I get 2.2588, da, da, da. These are actually the same number. When you have these square roots of the square root, sometimes they simplify, and this is an example. This one can be simplified to here. The algebra is kind of sticky, so what I'm going to do on the test is let you put either answer. On these kind, you can either solve them with the half angle identity, write this down, or you can solve them with the double angle identity, put this down. Let's not do ticky-tack long algebra to reduce that. I'll allow you to leave square roots to square roots, even though somehow, in some sense, this is a little weak. So be aware that you can use for any multiple of 15 degrees, either a double angle identity or a half angle identity. And they both work, but they can give answers that look different. And then the decimals, you check them. Sure enough, they're the same. Well, one last comment on here. Suppose I said if, I have to do a quick one here. If cosine of theta is 3/7, what is secant of 1/2 theta? Oh boy. I don't have a half angle identity for secant. What should I do on that? What you do is you say secant of 1/2 theta is 1 over cosine of 1/2 theta. It gets too much to memorize all 3 more half angle identities and 3 more double angle identities. So if you need a half angle or a double angle problem of a secant, cotangent, or cosecant, you just use 1 over the corresponding function whose half angle identity you do have. Now cosine of 1/2 theta is square root 1 plus cosine theta over 2, plus or minus. Right? And now you've derived the sine 1/2 theta formula. Right? You don't memorize it, you just write it as 1 over cosine. Here's the half angle formula for this. 1 over the square root just becomes the square root upside down. 2 over 1 plus cosine theta. Right? 1 over a quotient, you just turn the quotient upside down. There it is. This is the half angle identity for secant. And so you can just plug in cosine theta. Do we want plus or minus? I can tell you the quadrant, so I'm going to need to put it up here. Let's say it's quadrant 1, just to keep the problem short. If it's quadrant 1, then everything's positive. Right? And we'll write this as square root of 2 over 1 plus 3/7. And we're out of time, so I guess I'd better say you simplify it by multiplying top and bottom by 7 and call this 14 over 7 plus 3, and multiply top and bottom by 7. And it's square root of 14/10. That reduces to square root of 7/5, I guess. That would be a good answer, and maybe you want to rationalize it. That's it. What I'd like you to do then is, if you haven't tried the sum and difference identity, 7.2, make sure you do those. That's 1 through 5 and 7. I left out a couple of those in there. Actually, do 1 through 7. That's what I said. 1 through 7. 1 through 7. And then on 7.3, you want to look at 2 through 9. That's 2 sections. That's because this one is a review. This is the one we did before, but I said, don't do the homework yet. Because, right, you're going to study for the test. Now do it. And as you have time, do these double and half angle identities 2 through 9. We'll probably do just a little bit more of those next time. Let me know how those are working out. Come see me on office hours or whatever. Not very many people are showing up there, so you should get in. Thank you.